What? It's time for math class already? Let's do some math.
Calculus, early transcendentals. I can't wait to learn about calculus. You make me go mental. Logarithms aren't easy for me. When limits got you down and your mind won't work at all, don't worry about it, baby. Here comes L'Hopital. Calculus, early transcendentals, hyperbolic coaster catenary. Calculus, learn real world models when you make it to Calculus 3.
Howdy, calculus students. Today is a really special day because today we're going to learn about the derivative. The derivative of a function reveals in very fine detail the behavior of a function. For example, it tells you where the function is increasing and decreasing. It tells you where the function has minimum and maximum values. It tells you how fast the function is changing. It tells you a lot of stuff about the function. Today we're going to define the derivative and begin to learn it as a concept.
Hello. Today's topic is the derivative. The derivative is sort of the center of our attention for the rest of this class. And there is so much good stuff you can do with the derivative. And so it'll be exciting to start seeing that. We've already seen the derivative actually. We just didn't call it the derivative at the time. Recall we were previously talking about instantaneous velocity. We used the idea of instantaneous velocity to introduce the idea of limit. Like, why might we want to take limits? Let me remind you how that worked. So for instantaneous velocity here, the idea was, well, we know how to take average velocities over an interval of time. So then the idea was, let's take average velocities over smaller and smaller time intervals, sort of centered on some sort of point in time that we're interested in. And then we'll have something called instantaneous velocity. So it went something like this. So we have our V average was, you have a position function, s of t, which I've got represented graphically there on the left as a for example. And the average velocity over some interval, let's say from a to t on the t-axis there, was you would just take the displacement, which would be your terminal position, s of t, minus your initial position, s of a, and then you divide by the elapsed time. And then the idea was to pass to the instantaneous velocity, we would look at this interval here from a to t, and imagine that's getting shorter and shorter and shorter, and so we could take a limit as the t value on the right approaches a, on the left there, of the b average on the interval from a to t. And of course that's the limit as t goes to a of s of t minus s of a over t minus a. So this limit that we're looking at right here is an example of the derivative. In this case it'd be the derivative of s at t equals a. And you know, when we were doing this example of instantaneous velocity, we couldn't help but notice that when we looked at this line that went from the point where t is equal to a to the point on the right where t is just t, if we looked at that line right there, that so-called secant line, that the average velocity was just the slope of that line. Because remember, to calculate the slope of a line, you just do the difference in the y values over the difference in the x values, right? And you can see by looking at the coordinates of those 2 points that green line goes through, that's exactly what it's doing. So the average velocity was the slope of a secant line. And so we had this geometric version of this, or a geometric interpretation of this. So let's just stop thinking about velocity in particular for a moment and just think about a general graph. Just like we did above, take that line that goes through the point, like the 2 points on the curve like this. In this particular case, the 2 points are a comma f of a, and x comma f of x, and we have this secant line here, then the slope of that secant line is the difference in the y values. That'd be f of x minus f of a over the difference in the x values, so x minus a. And then the idea was, if we wanted the slope of the tangent line, so the tangent line is that special line that sort of just touches the graph in that one place there. Do my best to draw it here. Something like that. So we've got this tangent line. If we wanted to get the slope of the tangent line, well, that's tricky just to get it on the basis of that one point, because to get the slope of a line, you need 2 points on the line. And we only have 1 point on the line, so the idea was, let's look at this interval here between a and x and pretend that that interval is getting super, super short, so that if x was this point like here really close to a, then these 2 points would be so close together on the graph that the secant line through them, would be very close to the tangent line. You can see that those secant lines get closer and closer to being the tangent line as you move x closer and closer to a. So the slope of the tangent, m tan, we could get as the limit as x approaches a of f of x minus f of a over x minus a. And when we compare that to what we were doing with the velocities, it's the same limit, right? The only difference is the variable before was t and now the variable is x, but that's just a name. It's really the same thing. So again, this is an example of, this would be the derivative of the function f at x equals a. So it turns out though that this idea that we're calling the derivative is so important and comes up so much that let's just give it a special name. Well, I already did, the derivative. Let me give you the official definition here. Here's our official definition of the derivative of a function at a point. So the derivative of f at a, and we're going to adopt this notation here. F prime of a indicates the derivative of f at the point a. The derivative is the value of this limit right here that we saw previously, provided that that limit exists. Now we know from our experience in calculating limits that sometimes limits just don't exist. Sometimes the left-hand limit doesn't match the right-hand limit, for example, or maybe it goes to infinity, or maybe there's some oscillation, something weird could happen. So if that limit does exist, though, and it comes out to a single value, then we say the function is differentiable at the point. And a function being differentiable at a point is very good thing. You may notice here in this definition there's an alternate formulation of the derivative. It turns out, though, it's the same thing. It just looks different. Let me explain the second limit here, what the deal is with that. On this one here, if you would just you sort of make a substitution. You go, well, if x is equal to a plus h, all right, then as that h goes to 0, well, let's say it this way. As x goes to a, h goes to 0, right? Because if you think about it, if you took that x equals a plus h and solve for h, you'd have h is equal to x minus a. And so if x is getting close to a, then, h is getting close to a minus a, which is 0. With this substitution, this fraction f of x minus, well, let's put the limit out front. Limit as x goes to a, f of x minus f of a over x minus a becomes, instead of x is going to a, you've got h is going to 0, because we just pointed out that as x goes to a, h goes to 0. And then f of x becomes x is equal to a plus h. And you still have f of a there just the way it was before. And then also the denominator x minus a, as we pointed out up here, is just equal to h, so that becomes h there. So the second limit there that we have in blue is just the result of substituting in place of x, a plus h, and then changing the x minus a to just h, and observing that as x goes to a, h goes to 0. So it's just a substitution. It turns out, though, that sometimes that's a more convenient way to look at the derivative, and so that alternative formulation is pretty handy. And as we pointed out on the previous page, whenever your function's the position function, then the derivative, s prime of a, becomes the instantaneous velocity at that point. And then if you're just thinking about the graph of a function, f prime of a is just the slope of the tangent line. So already we have two interpretations of what this derivative is. Geometrically, it's the slope of the tangent line, and dynamically, it's if you have an object in motion, it keeps track of velocity. So for example, so that we can practice calculating those kind of limits, let's do this example here. I want to use the derivative to find the instantaneous velocity of an object whose position function is s of t equals negative 16t squared plus 40t, and at a particular time, t equals 2 seconds. And the position there is being measured in meters. So the instantaneous velocity we saw is really just the derivative of the position function, and we're looking for the derivative at time t equals 2, so it'd be s prime of 2. And then according to our definition of derivative, this is the limit as t approaches 2 of s of t minus s of 2 over t minus 2. And so then to work out what this limit is specifically, I need to substitute into the formula for the function. So s of t is negative 16t squared plus 40t, and then I do minus s of 2. So s of 2 would be negative 16 times 2 squared plus 40 times 2, and that's all over t minus 2. And I'll keep going here. I'll have to do some reduction. So it looks like I'm going to have negative 16t squared plus 40t. And then, let's see the constant term here. We've got negative 64 plus 80. Looks like we're going to have a minus 16 here over t minus 2. And then next, I could factor out a negative 8 from the numerator, looks like. So if I factor a negative 8 out up there, then I'll have be a positive 2t squared, and then negative 5t minus plus 2, all divided by t minus 2. And then limit as t is going to 2 here, negative 8. Hopefully I can factor that numerator so that the t minus 2 and the denominator will cancel. So if it's going to factor, it's going to have to factor like this, I hope. Looks like we can factor it as 2t minus 1 times t minus 2 in the numerator. So yeah, you get negative 4t and a negative t, so you get negative 5t in the middle. Okay, it works out. And then you see that you can cancel those t minus 2's, and then now you're just left with taking the limit of negative 8 times 2t minus 1, and I see that, that's a simple polynomial function that I can just substitute directly into to get the limit. And when I substitute, I get negative 8 times 3, so negative 24, and then the units are in meters per second. So we just calculated a derivative to get instantaneous velocity. And in a similar vein, we could use the definition of derivative at a point to find the equation of the line tangent to the graph of f of x equals 1 over x at a equals 2. If I just do a quick and dirty graph over here, y equals 1 over x looks roughly like this. And then so at, 2, the tangent line is going to look something like that in red. And so I want to find the equation of such a line. When you're hoping to find the equation of a line, you need a point on the line and you need a slope. At this point, we do have a point on the line, the point 2 comma f of 2, which is 1/2, is the point of tangency. But we need to find the slope, but we know that the slope is the derivative at the point in question. So let's calculate that derivative. So our m tan is really f prime evaluated at a equals 2. And then the definition of derivative says this will be the limit. Let's do the h is going to 0 version. So that's the limit as h goes to 0 of f of a plus h. In this case, a is 2, so 2 plus h minus f of a, which is 2, all over h. So this limit should give us the slope of the tangent line, because that's the derivative at the point 2. Okay, let's see how this works out. So this will be the limit as h goes to 0. f of 2 plus h, that means put 2 plus h in the formula for f of x, which is 1 over x. So we'd get 1 over 2 plus h there. And then minus f of 2, that'd be 1 over 2. And then that's all divided by h. Now, we're dividing all this stuff by h is the same thing as multiplying by 1 over h. So we can make this somewhat less compound of a fraction. I'm going to write it this way. Just seems a little easier to look at to me. All right. Now what I'm going to do is get a common denominator in this expression. And the common denominator would be 2 times 2 plus h. That'd be your common denominator. And so, I would need to multiply that first fraction by 2 over 2 to get that denominator of 2 times 2 plus h. And the second fraction there, I need to multiply by 2 plus h over 2 plus h. And if I do that, I'm going to end up with, still got that 1 over h out front there. I'll have 2, and this will all be over 2 times 2 plus h. I'll have 2 minus, and then 2 plus h from the second fraction. So that's what it looks like after you get a common denominator and combine it into one fraction. And then, of course, you can simplify a bit in the numerator. I notice that after I distribute the minus sign over the 2 plus h, I get a negative 2, and so it cancels the positive 2 that's there, and so I just end up with negative h in the numerator. And then I have 2 times 2 plus h in the denominator. Oh, good. Check it out. Those h's can cancel. And that was what was giving us a 0 in the denominator, so that's good that that happened. That was the sort of thing I was looking for. And now I'm just taking the limit as h goes to 0 of negative 1 over 2 times 2 plus h. And at this point, this rational expression, if I plug in 0 for h, it doesn't cause 0 in the denominator, so I can just evaluate it by direct substitution. And so I get the limit as h goes to 0. No, I'm going to go ahead and evaluate the limit. So substituting in h equals 0, I get negative 1 over 4. Okay, so negative 1/4 is the slope of that red line up there, which makes sense. I was expecting it to be a negative number. Yeah, so negative 1/4 seems like about right to me. So now that I have the slope and we have the point 2 comma 1/2, and so if we want the slope of the line, we can use this old formula, the so-called point slope formula. Y minus y0 equals m times x minus x0, so-called point slope formula. And we get the equation for the line is y minus, so when the x naught and the y naught are coming from the point that you have on the line, so this 2 comma 1/2 over here is my x naught, y naught. So y minus y naught, that's y minus 1/2. And the m is our slope of our tangent, so negative 1/4. And then you got x minus x naught. X naught is 2. And you could just leave it like that, or sometimes people like to solve for y. And so in this case, I'd have y equals negative 1/4 x. And then there's a plus 1/2 and a plus another half, so plus 1. So either way, either one of these answers would be fine. The next slide here is about generalizing this idea of instantaneous velocity. So velocity is is an example of what we call a rate of change. Velocity in particular is the rate of change in the position function, how fast the position is changing over time. But we can have other things that are changing over time, or maybe with respect to some different kind of variable. Like you can have populations changing over time. For some sort of animal, or you could have the volume of something is changing over time, like if you have some sort of tank that is filling with water. So we can measure all kinds of different rates of change, and so we need to have a few definitions of what we mean by rate of change. So if you have some function y equals f of x, and it's defined on some interval a to x, then this first fraction here, f of x minus f of a over x minus a, so that looks familiar, right? That's just the slope of the secant line that we were looking at earlier. We call that, when we're thinking about change, how fast the function is changing, we call that the average rate of change in f over that interval a to x. And then if we take the limit as x approaches a to get those, try to get down to an instantaneous rate, We call that the instantaneous rate of change. So this limit right here, which before geometrically was the slope of the tangent line or the derivative, that's your instantaneous rate of change in f. So using our newfangled notation for derivative, in other words, f prime at a is the instantaneous rate of change at a. So here's an example of a different kind of rate of change that we might want to look at. So in this example at the bottom, we have a leaking tank of water, contains a certain volume of water, and that volume of water here is given by the function v of t. So v of t equals 100 minus t squared cubic feet of water at time t in minutes. And of course you can see by the time you get to 10 seconds, there's no water left. So the interval over which this function makes sense is 0 to t. And so then we could ask questions about average rates of change and instantaneous rates of change based on this function. So the first question is, what's the average rate of change between time t equals 0 and t equals 5? Well, we should be able to handle that. So the average rate of change would be v of 5 minus v of 0 all over 5 minus 0. That's the fraction. If I go back up here to the definition in blue, if you want to do the average rate of change over the interval from a to x, you do f of the right-hand endpoint minus f of the left-hand endpoint of that interval in the numerator, and then you just do the length of the interval in the denominator. And that's exactly what I did here with v. And so then, we just have to calculate what's v of 5. Well, v of 5 would be 100 minus 5 squared. So that's 100 minus 25, or 75. And then v of 0 is 100. And then over 5 minus 0. So that looks like negative 25 divided by 5, so that'd be negative 5. And the units here, because in the numerator of this fraction that we were just computing, the numerator was measuring volume in cubic feet, and the denominator was in minutes, so the units here are cubic feet per minute. So it's not a velocity, it's a different kind of rate of change. It's a change in volume over time. And notice that the solution that we got is negative. And that makes sense because this tank is losing water, so its volume is changing in a negative way, right? So our rate of change being negative 5 makes sense. It's losing water at 5 cubic feet per minute. And then for part B, so since we're asking the question of how fast is the volume changing when t equals 3, so now we're asking about what's happening at a particular moment in time. And if we're asking about what's happening at how fast something's changing at a particular moment in time, that's when we have to use the derivative, because the derivative gives us instantaneous rate of change. So the instantaneous rate of change would be v prime of 5. And we know that's the limit as h goes to 0. And then since we're doing it at 5, it'd be v of 5 plus h minus v of 5 all divided by h. And so we have to work out this limit here, but we're going to do it because we're good at limits at this point. So v of 5 plus h, so that would be 100 minus 5 plus h quantity squared minus v of 5 is, well, we calculated that a second ago and it came out to 75 all over h. And I wished I could do direct substitution, but I can't right now because I would get that h equals 0 in the denominator. But so hopefully we can do some manipulation to make that h in the denominator cancel. I'm certain that we can. If we expand out what we have in the numerator there, we're going to have 100, and then when you multiply out the 5 plus h squared, you'd get 25 plus 10h plus h squared. We got to be sure to distribute that negative across those terms. So let's not make an error with signs here. So I'm going to have a negative h squared minus 10h. And then if I keep track of the constant terms in the numerator, it looks like I've got 100 and then a minus 25 and a minus 75. Hey, those constant terms all cancel one another out. Great. Oh, so this is looking good because now I see that I can factor h out in the numerator and cancel off the h in the denominator. And so now I'd be looking at negative h minus 10. Well, after canceling off the h, yeah, I'd be left with negative h minus 10. And now I can substitute in h equals 0, no problem, and I just end up with negative 10. And again, the units here would be feet cubed per minute. And I believe that answer makes sense. Coming out negative was good. So we're going to see as we start doing more applications in this class involving derivatives that there are all kinds of rates of change that we might want to consider. We might want to measure how fast the money is changing, how fast some sort of physical thing like electricity is changing. There's all kinds of applications of derivatives. It's very ubiquitous in science and economics. All right, so let's see what else we have here. Yes, the derivative as a function. So the idea here is that, we know how to calculate the derivative at any given point that we want to, the value of a. So I could do the derivative at x equals 2, or I could do the derivative at x equals 4. But each time I would do it, I have to do a separate limit. So what we'd like to do is just come up with a function that we can just calculate once that gives us the derivative, and then we can just plug numbers into that formula. So let me show you what I mean. Just to remind you of our definition of derivative here, if we use the version with h is going to 0, it looks like that. And the point here is that just notice that if you just replace a, which we're kind of thinking of as a specific point, with the variable x, you end up with this limit. F prime of x equals limit as h goes to 0 of f of x plus h minus f of x over h. So here, instead of thinking of x as a specific thing, we're thinking of it as just a general variable. And so, as it turns out, we can calculate that limit, and it gives us a function called the derivative function. So when we just talk about, in general, the derivative of f, and we're not talking about at any particular point, we're just the derivative of f as a function is this limit. It's the same limit we were really doing before, just using x instead of some specific value like 2. And it's the same as before. Whenever that derivative exists, then you say the function is differentiable at the point x. Something that's a little bit different now is we talk about differentiability on an open interval. When we say f is differentiable on an open interval I, it just means that f is differentiable at each point in the interval I. So having a function that's differentiable on an open interval turns out to be kind of like before when we said, it's important to have a function that's continuous on some closed interval or just on some interval. It's often very important that we have a differentiable function on an open interval, turns out. But we'll worry about that as it comes. Right now, though, I just want you to see how the derivative function works and see some examples of computing it. So let's start with a function f of x equals square root of x. And here we have to have, in order for this to make sense for the derivative, we need to have x greater than 0. I just want to calculate the derivative, so let's see how that goes. F prime of x, according to our definition right up here, just above, it's the limit as h goes to 0 of f of x plus h minus f of x over h. So let's carefully do this. I think, when I first saw this formula, I was confused by it. I always got mixed up about what I was supposed to do with that x plus h. But I think it's helpful that you break this numerator up into two pieces that you think about separately so you don't get confused. Sometimes it's even helpful to go off to the side somewhere and go, okay, what is f of x plus h? F of x plus h just means to put x plus h in place of x in the formula for f. So f of x plus h would be the square root of x plus h, like that. So I'm putting x plus h in place of x in the formula. And then you get your f of x is square root of x. And so then in the numerator, I just need to take the difference between those two things. So it'd be square root of x plus h minus square root of x, all divided by h. Well, here we have a limit involving some radicals. And we know most of the time with radicals we can do direct substitution. Just so long as after you substitute, you need to be getting a positive value inside the radical. And also, you can't direct substitute if you get 0 in the denominator. So our issue right now is the 0 in the denominator. But, we played around with doing limits of radicals before, and the standard trick when you're dealing with radicals and a limit that's giving you some trouble is to try the conjugation trick. So I'm going to try multiplying this fraction here by the conjugate of what we have in the numerator. So that'd be square root of x plus h plus the square root of x. Of course, I've got to multiply by the same thing top and bottom because what I'm really doing is multiplying by 1. And it's okay to multiply by 1 because it doesn't change the actual value of the expression you're dealing with. You want to keep it. You want it to be equivalent but looking different. All right, so if I do the multiplication in the numerator, the whole point of multiplying by conjugate is to get rid of the radicals, right? And whenever you multiply that out, what it comes out to is x plus h and then minus x in the numerator. And in the bottom, I'm just going to leave it as x times the quantity square root of x plus h plus the square root of x. I didn't multiply the h out because remember, the whole point of doing this is to try and get h to cancel away. So if I want h to cancel away, I don't want to distribute it and sort of muddy the waters. I want to keep it separate so that I can easily cancel it. Okay, so then if we simplify a little bit in the numerator, we see that those x's cancel and you've got h up there. And then you conveniently got that h sitting in the bottom ready to cancel. So let's cancel those h's off. As soon as I cancel that h off, I'm feeling really good about life because now I can see that the limit evaluates by direct substitution. If I plug h if I put 0 in for h, I'm not going to get 0 in the denominator anymore. I did drop a sign here though. I'm not going to get 0 in the denominator. I'm going to get square root of x and then another square root of x, so 2 square roots of x. And also, I said x was greater than 0 at the beginning, so I know that the denominator is not going to be equal to 0. So I can do this, and I end up just getting 1 over square root of x plus 0, and then plus square root of x again. So that's the direct substitution of h equals 0 in there. And then I could just write that as 1 over 2 square root of x. At this point, I've got f prime of x, derivative function is 1 over 2 square root of x. So this is really cool. So I just calculated this limit once. So I can do all kinds of derivatives at points now, like f prime of 1 is equal to 1 over 2. F prime of 4 is 1 over 2 times the square root of 2, so 1/4. And so on. I can calculate all the specific derivatives at points that I want just by plugging in for x in this formula that I just came up with here. So this is kind of cool, right? It's much more efficient. I only have to calculate the derivative once, get a formula for it, then I can use it to plug in specific values as needed. Whereas before, when we did, say, this example here with the volume of water in the tank, we did the derivative at 5 here as one limit. If I had asked you a part C, like how fast is the volume changing at t equals 7, then you would have had to do a whole other limit before. But now, you would have taken the approach, well, why don't I just do v prime of x, and then I can just plug in whatever x values that I need to. So this is nice. Okay, one more example of, calculating a derivative function to answer some sort of question. In this particular problem, we're going to use the derivative to find the equation of the line tangent to the graph of f of x equals the square root of the quantity 3x plus 1 at a equals 8. So I could go back to my definition of derivative at the point and use that to get the slope of this line. But I'm going to go ahead and do the derivative function and then just plug in 8 after I get done. So let's do f prime of x. F prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. And like I told you before, I find it helpful, especially when you're first getting started at this, to break up these two quantities in the numerator. Maybe go to the side and do them separately so you don't get them sort of, mixed up. What is f of x plus h? Well, f of x plus h just means put x plus h in place of x in the formula for the function. So that would be the square root of 3, and then in place of x, I'm going to put x plus h. And I still have that plus 1 there. So that's your f of x plus h, and then f of x, just repeating what's already written there, it's the square root of 3x plus 1. So these are the two things that I'm subtracting in the numerator. So now that I've got them sort of separate in my mind, let's subtract them separately here. So we get square root of 3 times x plus h plus 1 is the part in green, minus the part in blue is just square root of 3x plus 1. And then that's all over h. Now this problem is similar to what we were seeing in the previous problem. We got a limit that we want to evaluate that involves radicals, so we're going to do the conjugation trick. So I'm going to multiply times square root of 3 times x plus h plus 1 plus the square root of 3x plus 1 all over itself, so that we're really multiplying times 1. And whenever we multiply that out in the numerator, we end up with 3 times x plus h plus 1 minus 3x plus 1. And the whole point of the conjugation trick is to get rid of the radicals, essentially. And then you got h, but I'm not going to distribute it, times this quantity 3 times, or square root of 3 times x plus h plus 1 plus the square root of 3x plus 1. Wow, that looks like a mess. But, you know, I think you can see that when you distribute the 3 right here, you're going to get 3x plus 3h. And over here, after you distribute the negative, you're going to have negative 3x minus 1. And so you can see some things are canceling. The 3x and the negative 3x are canceling. The plus 1 and the minus 1 are going to cancel. And all you end up left with in that numerator is 3h. And then you've got h times all that mess in the bottom. And we see that now it's time to do some canceling. Get my canceling stick out here. And now the limit that I want to evaluate doesn't have the h in the denominator, causing me problems because I want to substitute 0 in there. So I end up with 3 in the numerator, and then square root of 3 times x plus h plus 1 plus square root of 3x plus 1. And I see that I can substitute h in there, and I won't be getting 0 in the denominator. And then when I substitute h equals 0 in right there, I just end up with 3 over the square root of 3x plus 1 plus the square root of 3x plus 1. And I see that I've got the same expression twice in the denominator, so I can write that as 3 over 2 times the square root of 3x plus 1. So now, since I have h prime of x, not h prime of x, f prime of x, f prime of x is 3 over the 2 times the square root of 3x plus 1. Now, in the problem at hand, I was being asked to figure out what's going on at a equals 8. I want to find the equation of the line tangent to the graph at a equals 8. So I want to do f prime of 8 to get the slope. So the slope of my tangent line that I'm interested in is f prime 8. And so all I have to do is plug 8 into the formula that I just found. And if I plug 8 in for x, I'm going to get 25 inside the radical. So I'm going to get 3/10 for the slope of my tangent line. My point of tangency is 8 is the x-coordinate, and I get the y-coordinate just by putting 8 into the function, the original function, not the derivative. The original function was square root of 3x plus 1, so I put 8 into the original function at the top there. I just get square root of 25 is 5. So my y-coordinate of my point of tangency is 5. And now I can do the point-slope formula, and the equation of the tangent line becomes y minus 5 equals then the slope 3/10 times x minus the x-coordinate of the point of tangency. I'm just going to leave it like that right there. If it were convenient to do so, for whatever purposes we had in mind, we could solve that for y, but right now I don't have a purpose for doing that, so I'm just going to leave it like that. All right, so moral of the story here is that we now have this ability to calculate a derivative function that we can plug any specific values that we want into it, and that after you calculate so you only have to do that once. To calculate the derivative function is a one-time ordeal, but once you have it, wow, you can plug stuff in it all day long. And you also start to see that, you know, for specific kinds of functions, you get general formulas for derivatives. Like, for example, on the previous page, we did, like, hey, there's the square root function. I now know, once and always, that the derivative of the square root function is 1 over 2 square root of x. You could think of that as just a general fact. It's not the case that every time I need the derivative of the square root function that I need to recalculate it. I've already calculated it once. I'm going to get the same answer every time, right? So sometimes it's convenient just to remember, oh, for this basic kind of function, this is what the derivative is. So it's a fact that you can keep using over and over into the future, which is kind of nice. Okay, notations for derivatives. You know, calculus has a fairly rich and interesting history. In fact, there are books written on this very topic. I think in the YouTube video here, I may place some links at this point in case you're interested in the history of calculus a little bit. But because of this rich history that calculus has, lots of different notations for derivatives have evolved over time. You have to remember that, this concept of derivative, it's been around a pretty good long time, but I think the sort of modern formulation of it sort of came around in the 1600s. I think the derivative itself was actually invented a bit before Newton and Leibniz, the inventors of calculus. Even the concept of derivative was around before then even. But I think you had one of the inventors was British, and then another of the inventors was, I guess, German. And so you had the continental Europe and the British, and then, of course, they were separated by geography and politics, and so things evolved differently over time. Anyway, you should check out some of that history. The first notation, the one that we've already been talking about, is prime notation. The setup here in all of these things that we're going to be talking about is that our function, we're giving it a couple of different names. So y, when we say y equals f of x, we're giving that function two names. One name is, we're calling it y, sort of for short. And then f of x, f is really the name of the function, right? Kind of like when you talk about sine of x. The name of the function is sine, and sine of x means put x into the sine function. So it's pretty common for us to name our functions, give them two names. And so when we're doing prime notation, we could call the derivative y prime, so the derivative of y, or y prime of x if we want to emphasize what the variable x, what variable we're talking about. And similarly, we can do f prime or f prime of x if we want to emphasize the variable. And if we want to talk about the derivative at a point, we can do y prime of a or f prime of a. So that's the notation that we've already been doing. The only new thing being is that, hey, maybe we give the function another name, y. And I have to emphasize here also that y is a name, and it's not the only name you can possibly name something, right? I might call the function p if I'm talking about profit, or I might call it v if I'm talking about volume, or these sort of things. So you give functions names that are related to what the function's purpose is. This dot notation we're not going to use in this class. I'll never use it, but I did want to tell you about it just real quick because it does come up in physics. So if you were taking a physics class, you might see them putting dots on top of the function names. Means the same thing as the prime, just means derivative. We will use this operator notation here from time to time. So the operator notation, you put a D, big D, and then the subscript is the variable name, whatever the variable of your function's name is. So, we tend to use x as our general variable, but it could be a t or whatever, right? So dxy, or you could say dx of y of x. So the idea here is this big D is we're thinking of it as this operation that's being performed upon y or being performed upon f. And then we have this notation for derivative at a point, which is, it's a bit more bulky than what we had before, but if you want to talk about substituting something into the derivative, you can just put the notation for the derivative there and then put a bar after it and then put what you want to substitute in for the variable. So x equals a. That means substitute a in for x into the derivative. So you get the derivative at the point. And then this last notation I think is the most mysterious in terms of why does it look that way. And I'll try to give you a quick explanation of why the notation looks the way it does. But actually, it goes even deeper than what I'm going to say, but I don't want to spend too much time on it. So so-called differential notation. dy dx, dy over d. So it looks like a fraction. For now, you shouldn't really think of it as a fraction. You should just think of this whole block of symbols means derivative. So dy over dx means the derivative of y. In the x that you're seeing in the denominator is sort of telling you what the variable is. So y is a function of x, so I'm taking the derivative of y with respect to the variable x is kind of the way that reads. Or you can kind of think of the d over dx as an operator, kind of like the big dx before, that you put in front of the function to calculate its derivative. And then, you can do the same thing with f or f of x there too. And then if you want to plug a number into the derivative, you can use that bar notation, just like we did before with the operator notation. So dy dx, put the bar, x equals a means put a in place of x after you calculate the derivative. Where this differential notation comes from is if you're thinking about a tangent line to the graph, for example, I've got this value x here, and I'm thinking about the tangent line at that point. So the way that we kind of get tangent lines as limits is what we really do is we kind of calculate the slope between two very, very, very close together points on the graph, right? There's like x, and then there's something very nearby to x, so we might call that x plus dx. So dx here is understood to be a very, 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 very small change in x. So if I do x plus dx, I mean, they're microscopically close together. In fact, dx is called an infinitesimal. And so then I move over by dx, and then I look at this, I get the second point on the graph, and the amount that you move up, or the amount that the function changes over that very small infinitesimal interval is called dy. So dy there is the change in y as x changes by dx. If you do dy over dx, you're going to get the slope of that line, because that's how the slope of the line works, right? It's just how much the y changes on the line and divided by how much the x changes on the line. And so that's why you can kind of think of dy dx as it really is a fraction. But at this point, we don't have any means for dealing with the numerator and the denominator of that fraction separately. So at this point, when you see dy over dx, just think of it as the derivative, as a single thing. Later, whenever we start talking about infinitesimals, then we can think of it more as a fraction. But anyway, look, there's a lot of different notations for derivative, right? And you need to be aware of all these different notations because they get used interchangeably. Besides, we're not going to use the dot notation in this class, but the other three, yeah, we're going to use all the time interchangeably, and just part of the course. And it has a lot of historical reasons also that I think you'll find interesting if you look into it. So for example, here's a function y equals x squared, and I'm going to calculate the derivative, dy dx, and then also find the derivative at the point x equals 2. So we already know how to do this. It's the same thing we've already been doing. We're just emphasizing the new notation here. dy dx, that means derivative, sort of the derivative function. So that would be the limit as h goes to 0 of, I'm going to write it as y of x plus h minus y of x over h. So you see, I didn't have the name f in play here, so the only thing I named that function was y. Y is x squared. So that's okay. So now what is y of x plus h? That just means put x plus h in place of x in the formula for the function y. So you'd get x plus h quantity squared for the first term in the numerator there. Then you get minus y of x, that's minus x squared, and then all over h. And then we'll work at simplifying this fraction to the point where we can substitute in h equals 0. If we expand the square out that term in the numerator there, we'll get x squared plus 2 times x times h plus h squared. And then we still have that minus x squared there, all over h. Oh, good. I can see that those x squared terms cancel. And then I'm left with 2 times x times h plus h squared all over h. And you remember our goal is to sort of cancel off that h in the denominator so that we can substitute. And I see that, yeah, I can factor out an h in the numerator now. And that'll allow me to cancel off the one that's in the denominator. So let me get my canceling stick out. Cancel, cancel. That always feels good when you cancel that h out. Satisfying. And what I'm left with is taking the limit of 2x plus h. But now I'm not going to get any zeros in the denominator when I substitute in h equals 0, and I end up with 2 times x. So summary, dy dx equals 2x. That's our derivative function. And then dy dx at the point when x is equal to 2, well, that's easy. That just means put 2 into the derivative. So that's 2x evaluated at x equals 2. So 2 times 2 is 4. So now it's time to tie differentiability into something we talked about previously, continuity. So, nice theorem. And actually the proof of it is remarkably simple. I'm not going to prove it in this lesson, but I encourage you to look in your textbook at the proof. The proof's very short and very easy to understand. But it says, if you got a function that's differentiable at the point A, then it also is continuous. So differentiability implies continuity. That's nice because, look, we know we just went through several examples where we can see in how you calculate the derivative. If you're able to calculate the derivative, that means it's differentiable, right? So if you calculate the derivative and once you have the formula for it, you can just look at, okay, where is the derivative defined? And from that, you can see where the function is continuous. So this gives us kind of a shortcut for figuring out where a function is continuous. For example, the previous example that we just did for the function f of x equals x squared, we found that the derivative function was 2x, right? So then you just ask yourself, okay, if I'm wanting to know where is this function f of x equals x squared continuous, I can just look at the derivative and go, oh, well, the derivative is defined for all values of x. Then that means that f, the original function, is continuous for all real numbers x. Now we already knew that all polynomial functions are continuous for all real x. So this isn't a big surprise or anything, but the point of it is that if I want to think about continuity, one way that I can get at it is to look at the derivative function and go, well, derivative function, where are you defined? Sometimes it's easier to think about where is a function defined than to think about where is it continuous. You change your focus from the original function to the derivative and just go, where is it defined? And usually all you have to worry about for where is it defined is like, you just got to make sure to avoid places where you're dividing by 0, or maybe where you're getting negatives and radicals or something like that. So it's sort of an easier thing to think about after you calculate the derivative of where is it defined. But anyway, that answers the question of where is the function continuous. So for example, here's a function we haven't yet calculated the derivative of. I encourage you to take a moment, press pause on the video, and calculate the derivative of this function. In the interest of time, I'm going to go ahead and give you what the derivative function is here. So the derivative function for this, let's see, this is x to the 1/3. So f prime of x is going to be 1/3 times the cube root of x squared, it's going to turn out to be. So did you get that answer from your calculation of the derivative? I hope so. A little later in the class, pretty soon, you'll be learning some shortcut methods for calculating these derivatives, but at this point I hope that you calculated that derivative using the limit as h goes to 0 of f of x plus h minus f of x over h. Okay, so now I've got this derivative for the original function, and I can just look at that derivative and go, where is that derivative defined? So observe, f prime is defined for all x except x equals 0. So this tells me that f is not differentiable at x equals 0. I know that the function is differentiable everywhere except for x equals 0. So I know that f is continuous for all x not equal to 0, but I want to know what's going on at x equals 0. So I know the function is not differentiable at x equals 0, but that theorem up here does not tell me that if it's not differentiable, then it's not continuous. The only thing you can deduce, an alternate formulation for that theorem is that you could say that if the function is not continuous at a point, then it can't be differentiable there. So you could say if f is not continuous at a, then f is not differentiable at a. But knowing that f is not differentiable at a does not tell me that the function is not continuous. In fact, if I would go, let's take a look at the graph of the cube root function. This is what the graph of that function looks like, and it looks continuous at 0, right? The original function is defined at 0. What's going on there? Well, what's going on is that when you look at the graph of this thing, it kind of looks like this. And when you think about what's going on with the tangent line at this point, the tangent line is going vertical. And what is the slope of a vertical line? Well, it turns out vertical lines slope is undefined. We kind of think of it as having an infinite slope because, the slope is the change in x over the change, or the change in y over the change in x. On a vertical line, the change in x is 0. So when you try to do the slope calculation, you get division by 0. So it's kind of like the slope is going to infinity. And in fact, it is going to an infinity because you could do something like this. You could go, okay, it's like your m tan at 0. You could think of it as being the limit as x goes to 0 of the derivative. And if you calculate that, so that's an example of an infinite limit right there. So anyway, this function is actually continuous everywhere, but the derivative can't tell you about the point when x is equal to 0. So at that point, we have to think about it some other way. We could get the continuity of the original function just by going back to the original definition of continuity and just pointing out that the limit of the function equals what you get when you plug in 0, which is 0. Just wanted to point out that the derivative doesn't always give you every answer about continuity, but when it works great. In this example at the bottom here, I'm asking the question, is f of x equal to 1 over x differentiable at x equals 0? Well, I could use the theorem to immediately answer no without even calculating the derivative. 1 over x is not continuous at 0 because it's division by 0 there, right? So the function is not even defined. So I could say no, f of 0 is undefined, so f is not continuous at x equals 0, and a function that's not continuous at a point certainly can't be differentiable at that point, because if it were differentiable at that point, it would be continuous there, right? So since f is not continuous there, that tells me f is not differentiable at x equals 0. So I found out something about differentiability here without even calculating the derivative, which is kind of nice. So understanding this connection between differentiability and continuity is kind of nice. We can use it to our advantage sometimes. It's interesting to think about the ways that a function might be continuous but not differentiable. So continuous just means, intuitively speaking, that you can graph it without lifting your pencil. There's no jump or break or hole in the graph at the point. But even though there's not a jump or a hole or a break in the graph at a point, it still might not be differentiable. And so the places where a function might not be differentiable include sort of corner points, like we see on the left graph at the bottom there. So the absolute value function, you can show, is not differentiable at x equals 0. It's differentiable everywhere else, but it's got this one bad place where it's not differentiable. We can work that out algebraically. Maybe I'll do so in a moment. You can also have what are called cusps. Cusps are places kind of like what we saw a minute ago. They're places where the vertical line goes tangent. The tangent line goes vertical. In the middle picture, there's an example of a cube root function where the tangent line goes vertical at this one spot 3. And the difference between a cusp and a cusp is sort of like an infinitely sharp corner point. And then you can also just have places like in the cube root function where the tangent line goes vertical, like on the picture at right. So it's not a corner or a cusp, it's just a place where the graph momentarily sort of goes vertical, which causes vertical tangent lines to have undefined slope. And so that's why the derivative is undefined. So like, for example, with the absolute value function there, why does it have a problem at x equals 0? Well, let's just try to calculate the derivative and see what happens. So if we have f of x is the absolute value of x, then if I wanted to do f prime of x, it would be the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. So that's the limit as x goes to 0, h goes to 0, of absolute x plus h minus absolute value of x over h. We'd have to consider 3 cases about what the derivative would be. We can do the case when x is greater than 0. So I have to remind you that like the absolute value function, absolute value of x, remember that has this piecewise definition. It's equal to x whenever x is bigger than or equal to 0, and it's negative x if x is less than 0. So because of this, I have to consider cases. I have to break it into the positive part and the negative part, and sometimes it helps to do the part where it's exactly equal to 0 as a separate case too. So I'm going to do the case where x is strictly bigger than 0. In that case, your f prime of x, those absolute values in I can drop the absolute value symbol on it in that limit right here, because if x is larger than 0, then x plus h and x, since h is going to 0, I can assume that that x plus h is going to be positive whenever h gets small enough. So I can drop the absolute values there, and I just end up with x plus, doing the limit as h goes to 0 of just x plus h minus x all over h. Notice that that all just collapses down to 1. You're taking the limit of 1 because the x's cancel, and then you got h over h, and that's just equal to 1, so you get the limit of 1. And what that corresponds to on that graph up there on the left is that that slope is equal to 1 on that whole right-hand side of that absolute value function. And then similarly, you can do when x is less than 0 and your f prime. This time, because the x is less than 0, then those absolute values up here, when we were taking the derivative, we got it to this point, and we have these absolute values in the numerator. But if x is negative, then I can replace the absolute value stuff there with negative of that quantity. So this becomes negative quantity x plus h minus negative x all over h. And when you distribute the negatives around, you see that you got a negative x and a positive x in the top and a minus h in the numerator. So it ends up being negative h over h after you sort of simplify a little bit. And negative h over h is just negative 1, so you're taking the limit as h goes to 0 of negative 1, which is just negative 1. So that tells you, when you look at the picture of the absolute value function on the top left there, it's just telling you that the slope over here on the left-hand branch of that absolute value function is negative 1. But what's happening when x is exactly equal to 0? That's where it gets broken. F prime of 0 is just what I get. First, I'm going to put x equals 0 in our derivative formula. I'm going to get limit. So h goes to 0 of, it's going to be absolute value of h minus 0 over absolute value of h, or absolute value of h over h. And to do that limit, I would look at the one-sided and to get the two-sided limit, I'll look at the one-sided limits. So I'll do the limit as h goes to 0 on the left of absolute value of h over h. Well, if h is a little bit less than 0, then absolute value of h is negative h, and you get limit as h goes to 0 on the left of negative h over h, which works out to be negative 1. And the right-hand limit, since h is a little bit bigger than 0 here, the absolute value of h is just h, so you get limit as h goes to 0 on the right of just h over h, and that just works out to be 1. So check it out. The left-hand limit doesn't equal the right-hand limit, so that tells you that this limit right here does not exist. So in other words, f prime of 0 does not exist. The function is not differentiable there. And it's just because the slope of the tangent line's confused. The tangent line wants to be like, if you're coming in from the left-hand side, it wants to be like that, but then the tangent line wants to go that way, coming from the other side. So, the tangent, there's not a unique slope that you can sort of assign to the tangent line there. The tangent line's confused. So, and that comes out in the algebra the way I did it there. Anyway, we got this point of non-differentiability at x equals 0, and we can see graphically that that just means, oh, there was a corner there, or it's because there was a corner there. Corners and cusps really throw off the derivative, or any place where you get like a vertical tangent. Okay, I think I'm going to stop there, and our next lesson we'll be talking about ways to calculate these derivatives a little bit faster without having to use the limits. That'll be cool. Okay, until then.